Hi there, students. Well, since we had so much fun in the last lesson learning about logarithms and logarithmic functions, I thought we would continue that fun today and take a look at graphing logarithmic functions. So our essential question today is this. How is the graph of g of x is equal to a times the log base b of x minus h plus k, where b is greater than 0 and not equal to 1, relate to the graph of f of x is equal to log base b of x? In other words, if we look at the basic logarithmic graph and we transform it, what does that do to the graph? So just like with every other type of transformation of functions we studied, we always start off first looking at the parent function. And, really we're going to, just focus on, there's obviously infinitely many different logarithmic functions because it just depends on what the base is. We're going to focus on a couple of the common ones today. And the one that you see here in this introductory graph, that's already graphed for you, is the log base 2 of x. So they plotted some points here, but we can learn a lot about the graph just by looking at this specific one. And so you can see that this graph, which we looked at a little bit yesterday, is the reflection of an exponential graph because really, the logarithm is just the inverse of an exponential function with that same base. And so, this is a reflection of the graph of 2 to the x power over the line y equals x. And so on this graph, the logarithmic graph, what you're seeing is the ordered pairs that relate the result of raising something to the power to its exponent. So for instance, this point right here, the input is 8, and that's the thing we want to find what power we're raising to get that. So we would say that the log base 2 of 8 is 3 because we raised 2 to the third power to get 8. And so our ordered pairs here represent the input being the outcome of raising something to a power, and that's the input, and the output is the exponent itself. And the characteristics of the graph are, first of all, you can see that there is clearly an asymptote right here at the y-axis, or in other words, at x equals 0. And we can see that the domain is going to include only numbers greater than 0 because that asymptote basically cuts the graph there and it begins just after it. And the reason why that is because remember the inputs are, we're giving like the results of raising 2 to different powers, and of course we're never going to get 0 when we raise 2 to a power, and we're never going to get negative numbers. So there's this asymptote here at the y-axis, a vertical asymptote, whereas the exponential graph had a horizontal asymptote at the x-axis, or y equals 0. And then again the coordinates, some of the key coordinates would be from raising, or from the different results that we would get from raising 2 to different powers. So for instance, this point right here, 0.5 and negative 1, that's if we raise 2 to the negative 1 power, we would get 0.5. In other words, the log base 2 of 0.5 is equal to negative 1. Or this one right here, which we already talked about, that would be log base 2 of 8 is equal to 3. So again, what that looks like, how we get that coordinate is log base 2 of 8 is equal to 3. So 3 is the output, or the y value, that's the y, and the input is the 8, which is the x. And these coordinates are all the key values, or some of the key values that create the shape of that graph. So when we think about, again, we talked about the domain of this graph. So the domain, if we wrote it in set builder notation, we would say x such that x is greater than 0. And then the range, on the other hand, there are numbers below the x-axis, there's numbers above the x-axis, it crosses the x-axis, so that's all real numbers. And so it could be any number that's less than positive infinity but greater than negative infinity, so in other words, covering all real numbers. So if we were using the interval notation, or if we were using, let's say, in this case, set builder notation or whatever, our boundaries, it would be boundless, so negative infinity and positive infinity, or we could also say all real numbers. So that is one of the parent functions, that's log base 2 of x. Let's take a look at the next one, which is log of x. So remember, when we don't see a base listed, that means it's base 10. And so that means log base 10 of whatever we put in for our input will give us our output. And so if we completed this table over here, if I put in 0.1 for the input, in other words, 10 to what power is 1/10, I know that my output would be -1, so that gives me an ordered pair of 0.1 and -1. If instead the input was 1, so in other words I'm saying 10 to what power is 1, I know that that's 0, because when I raise 10 to the 0 power, I get 1. And so my output would be 0 on this one. And then, of course, if the input is 10, then I know that the exponent must be 1, because 10 to the first power is 10 itself. So if we were to plot these points, it'd be kind of difficult to plot the 0.1 and -1, but we just get really close, since we know that there's a an asymptote here at the y-axis, just like there was with the other log graph. We could plot really, really close to that, but and then the -1 would be the output. So we at 0.1 and -1, which would be right about here, at 1 and 0, and that's the x-intercept. So these don't have y-intercepts, these have x-intercepts, and then at 10 the output is 1, because again that's the exponent. So the graph is going to look, it's a little flatter than that other one because the base is larger, but otherwise the graph looks just like that. And so honestly, if we had to decide on just like a lower number of points to use here, we could have kind of got away without using this point right here, because we know there's an asymptote there at the y-axis. And so if we just had that x-intercept and we had that one point where the input was the base itself, and so the output was 1, that would give us a good graph, because we know that it would taper off as it's getting closer to that asymptote. So we could have also just done this with just these 2 points alone. So the domain is, we can see from the graph that it that does not go to the left of the y-axis, and so the x is going to be greater than 0. And again, if you want to be fancy, you can use your set builder notation. The range, on the other hand, is all real numbers. So different ways to represent that, we could use interval notation. So I could have done this, -infinity to +infinity. I could use set builder notation. I probably should be consistent with what I did for the first one. So if I'm going to use set builder, I'll use set builder here. So I'd say y such that y is less than +infinity, or just infinity, I guess, and greater than -infinity. And then if I had to also identify the asymptote, I would say that it is at x equals 0, which is the y-axis. Okay, let's take a look at one more, and this is another very, and I don't want to call it common, because we know when we say common with logs we mean base 10, but a very frequently seen logarithm, which is the natural log. So if I wanted to graph the ln of x, what I'm really doing is using a base of e, right? So I mean, we wouldn't really write the little base here, but that just reminds me that's really log base e. And so when I'm graphing that, again, I'm going to still have some of those same characteristics. I'll still have a vertical asymptote right there at x equals 0, and that's because I can never raise e to anything and have the result be 0 or negative. So I know that that sort of just ends there at the y-axis. The graph does not pass that. But as far as the other points that I want to put on my graph, I'm going to do kind of the same thing I just did. I'm going to think about the x being the input, and that means it's the result of taking e to the power, and then my output is the exponent that I'm going to be raising e to. So they, in the table here, chose to put in 1 over e, and then 1, and then e, and e squared. And they did say that 1 over e was about 0.368. But if I just put in the natural log of 1 over e in my calculator, it would actually tell me that it's -1, And that's because I know that a power of -1 means to take the reciprocal. So that would give me 1 over e. So that output is -1 for an input of 1 over e. If I substitute 1 in, so then again if the input here is, so I'm saying that that is actually the result of raising e to a power, and I get 1, that means the output must be 0, and that's because e to the 0 is 1. And if instead I had my input being e, so again, they strategically pick these to give you, good values here. And I know that the exponent would have to be 1 because e to the first power would give you e. And so then finally, if instead the input was e squared, I'd be saying log base e of e squared is, well, and so I'm asking the question, e to what power is e squared? And of course it would have to be 2, very clearly, right? So I could take these points now, and I could plot them on my graph, and I would see basically something that looks very similar to the prior two graphs, but because the base now is about 2.718, it's going to have a little bit different, steepness, I guess, as it curves, but the asymptote's going to still be the same. So when I graph that first one, it's about 0.368 and -1, so again, that's going to be pretty close to the x-axis, I'm sorry, the y-axis, so but that's going to maybe be right about there. And then at 1, 0, of course, again, these are going to all cross, just like the exponential base graphs or parent functions crossed on the y-axis at 0, 1. These are going to cross on the x-axis at 1, 0. And that's because if you have a result of 1, that means the exponent must have been 0, because anything to the 0 power is 1. And so for the next one, which is about 2.72 or 718, that's going to be 1. So maybe right about here, somewhere right in here, just a little shy of 3. And then they gave us one more, and that's out just a little shy of 8, so 7.39 and 2. So maybe right about here. And then we'd see our graph again kind of tapering off at that asymptote and going forward looking like this. Okay. So that's a pretty good sampling of, and you can see that the characteristics are shared. We looked at the domain and the range of this. It's going to be the same. Your domain is all real numbers. I'm sorry, oops, not all real numbers, but greater than 0, sorry, because again, there's nothing we can raise e to get 0 or a negative number. And then my range is, of course, all real numbers. So if you wanted to use that same inequality notation, we could write it like this, or you could say all real numbers with the symbol. Okay, let's go ahead and turn the page. So as usual, once we learn about these graphs and their characteristics, then we want to transform them. And we want to move them around, shift them, reflect them, things like that. So when graphing transformations of the log base b of x, so again, we use b just in general, so this really pertains to any log graph, where b is greater than 1, it helps to consider the effect of the transformations on the following features of the graph of f of x. The vertical asymptote, so of course we looked at the basic position of that is going to be at x equals 0 or the y-axis, and 2 reference points, and the ones that they suggest are not unpredictable. They're 1, 0, which is what we've seen is in every case of these parent functions is going to be the x-intercept, so that one's where it crosses the x-axis. So we'll take that as one of our reference points for every single one of these, just like we did 0, 1 on the exponential graphs. And then the other one would be b, comma 1, and b meaning whatever the base is. And that's because if the output, or the x value in this case, is the same as the base, the exponent's going to be 1, because anything to the 1 power is itself. So those 2 points are good key points to use, and then of course knowing where the asymptote is, that gives us really enough to determine where the graph's going to end up and what the shape's going to be. So the table lists these features as well as the corresponding features of the graph, and g of x is equal to a. Remember, a is always the vertical stretch amount. log base b of x minus h plus k. So remember, the h and the k are the slide amount, and the a is this vertical stretch. And if a is negative, it also means it's going to be reflected over the x-axis. So that's the first thing we're going to do, is we're going to go ahead and take a look at seeing if we can identify what transformations are happening. And there's one that's been done for us, so we're going to just take a look at that one. And then we will look at writing our coordinate rule and then transforming these points and plotting them to get our graph. And then we'll identify the domain and the range. And they do say for us to use set notation, so we'll go ahead and stick with that notation for now. So example A, my new graph they want me to produce is -2 times the log base 2 of x minus 1 minus 2. So I can tell right away that this thing's going to be reflected over the x-axis. It's going to be a vertical stretch. It's going to be a slide 1 to the right, because x lies to you, right? So it's going to the right, and then down 2. Now remember with the exponential graphs, when we shifted up or down, that was what affected the asymptote because it was horizontal. But in this case, because the asymptote is normally the y-axis, which is vertical, then the slide left or right is going to affect this one. So this is actually going to take the graph and slide 1 unit to the right, which is funny because they definitely do show this on the graph. I'll show you that this right here is the graph of the transformation. And then, of course, you see the original graph there on there, the parent function. And this definitely, goes along with the description we gave. But it's interesting because they seem to have drawn on this graph a dashed line at 3. So that's clearly not where the asymptote is. And you can clearly see it's right here at 1 to the right. So they moved it over 1 because of the horizontal slide 1 to the right. So now the vertical asymptote is at x equals 1. So that's my horizontal asymptote, or I'm sorry, vertical asymptote. And then I take my two coordinates that we talked about. So first of all, 1, 0, which is where the parent function would normally cross the x-axis. And we're going to write a coordinate rule, and then we're going to apply that. They didn't actually show the coordinate rule, so we're going to do that. And then, of course, they used the base. They plugged the base and 1 in. So that's our second point. Our coordinate rule would look like this. So we think about what's affecting the x. So the thing that's doing the x is moving it to the right. So our coordinate rule would look like this, x plus 1. And our coordinate rule for the y would be -2 times the y coordinate, and then -2. And so taking these coordinates and just, simply substituting them into for x and y will produce our new coordinates. So if I plugged in, and I kind of don't know if I love the table, so I'm going to just redo these real quick. So if I were to plug in 1 in for the x coordinate, I would get 2, and plug in 0 for the y, I would get -2. And so if we go over here, we can see where that point is on the graph. It's over here at 2, -2, right there on the graph. We also have that asymptote, which we can see happen from the horizontal slide. And then finally, if we take the other point, we take the 2, 1, which is the base, b, which is the input, and then 1 being the exponent. And we substitute those values in. And let's see, so that would give us 2 plus 1 is 3. And then plug 1 in for y, that's -2 times 1 is -2 minus 2 is -4. And you can see that's on there as well. Over 3 and down 4, there's that point. And sketching the graph along with that asymptote gives us the shape, the new shape of this graph. You can see here that the domain is now x is greater than 1, and that's because that shift to the right now is moving it to the so that it never goes below 1 or actually even gets to 1. But the range is always going to be all real numbers. So let's go ahead and try one on our own. So this particular one, I just wrote over. I got to erase that. So first of all, I can see that there is a horizontal slide, and that's going to go 2 units to the left. And that means that that vertical asymptote, which was at the y-axis, is going to move 2 units to the left now. Okay? So I know it's now at -2. X equals -2 is my asymptote. I'm going to go ahead and write my coordinate rule. They kind of have it embedded into this table, but we'll go ahead and write our own. So I can see what's happening here to the x is it's being moved 2 units to the left. So the net effect will be to take the x and subtract 2 from it. And then the y coordinate will be multiplied by 2 and then have 4 being added to it. So there's no reflection here. This is a vertical stretch. It's going to be a slide 4 units up and 2 units to the left. So we take our key points that we talked about, and those are 1, 0, which is always going to be on these graphs because that's going to be the x-intercept and any of the parent functions. And then because this one, it doesn't show a base, that means it's base 10, right? So the input is 10 and the output will be 1. So those are, again, the numbers that are on the parent function. So we're going to see what happens when we apply the coordinate rule to them. So plugging in 1, 0, if I put 1 in here and 0 in here, so 1 minus 2 is -1, and 0 times 2 plus 4 will give us 4. So that's one of our points. And then if I plug 10 in and 1 in, so 10 minus 2 is 8, and then plug 1 in, that's 2 times 1, which is 2, plus 4 is 6, and then 8, 6. So I'm going to come over here and plot my new points, so -1 and 4, so -1 and up 4, and then 8 and 6, so 8 and 6 would be right here, and I know that this is going to taper off near that asymptote like this, so my graph's going to be like that. So I can see that shifting nature. It went up 4, it went 2 to the left, and it stretched it. So that's a little bit steeper of a graph. Now my domain this time is going to be greater than -2 because of that shift to the left. But my range is going to remain all real numbers, so from -infinity to +infinity. Okay, so it's time, I believe, for a U-try. And so we're going to go ahead and turn the page, and we'll designate this next question as a U-try question. Keeping in mind you want to identify the asymptote, those 2 key points, sketch your graph, and include the coordinate rule. So go ahead and pause the video now and try the U-try question. Okay, so thanks for giving that one a try. So my coordinates that I came up with from the transformation rule of x minus 1 and then 1/2 x plus 2 were 0, 2, and 1, 2.5. My vertical asymptote was that x equals -1 because of the shift 1 to the left. And so I can definitely see on that graph that what I thought was going to happen, which is a vertical compression of 1/2, so it definitely looks flatter, the graph does, and the shift 1 unit to the left and 2 units up. I can definitely see that in the graph very clearly. Make note of the domain, x is greater than -1, and the range are real numbers. So the next thing we're going to take a look at, has kind of been the usual pattern of these lessons, is once we take a look at defining these functions and kind of applying them in some different situations, and then transforming their graphs after we look at their graphs, then we look at trying to model some real life situations. Of course, that's why we study math. So in this next section, we're going to look at writing, graphing, and analyzing a logarithmic model. Now, we're going to be using the regression method, which is utilizing the graphing calculator. So at this point, we're going to reserve this part of the lesson to do in class, because we've seen so many times all the kind of pitfalls of technology and things that can come up that if I'm not there with you to help get you on the right track, it could kind of impede your progress here. So we're going to go ahead and end the lesson now, and the rest of this we're going to plan to do in class, and so be sure to bring your graphing calculator, and I will see you next time.